Okay, we're really privileged to have our next speaker, Stan Williams, come and present. Stan is the Senior Fellow and Director of the Memristor Research Group of HP Labs. Stan is also the owner of 500 worldwide patents. So, Tom, no disrespect, but now he's the smartest guy in the room. So without further ado, I'm going to turn it over to Stan.
Thank you very much. Really appreciate it. So, first of all, I'm not exactly sure what I'm doing here, but thanks for inviting me anyway. What I'm going to do is I'm actually going to present to you my perspective on where computing is going. And I'm going to claim that computing is we've entered I'll call it a revolutionary period, where over the course of the next roughly 5 years or so, computing is going to change more in the next 5 years than it has in the past 60. We're going to see the first true revolution in computing away from the von Neumann architecture to something new, and I'll describe it. But in order to get away with this, I feel compelled to tell you why this is going to happen. And so what that means is I'm going to have to give you some physics tutorials along the way. Because I think it's important to be grounded at that level to make sure that it's not just some PR or flash, that there's reality behind it, and that you can understand what's coming and why it's coming and why it's going to unfold, or at least why we think it's going to unfold in the way that we're predicting. So that's my setup. Let's see. Now, practically everyone in this room, if not absolutely everybody in this room, makes their living from IT in some fashion. And so one thing that I would like to recommend to you is, if you have not read this book, Turing's Cathedral by George Dyson, I think it is an important book for people to read. If you make your living from computing, you should really read this book. The issue is, for the first 2/3 of it, you probably won't like it. It's challenging, to say the least, to get through, because George, actually, it's not written badly. It's written in a very, very curious way. What he's doing is he essentially is putting you inside an operating computing program. And so as you're reading, you are looping around, you are doing do loops, you're exiting, you're coming back, and it will drive you absolutely nuts. But the structure of the book itself is an allegory for what computing is today and how it came to be. Then, sort of in the last 1/3 of the book, what he does is he takes this experience, this rather harrowing experience that you've been through, and then he essentially starts to talk about what's happening with computing and where it's going in the future. And I'm not going to give the thing away, but he has some extraordinary insights into how human beings and computers are essentially symbiotically co-evolving, and how our genes are changing because of the way we work with computers. All right, so with that as a little tantalizing tidbit, let's see, where am I supposed to be pointing this thing? Okay. So let me just sort of jump into this now. So you've heard a lot of these issues about the new style of IT, but the fact is that with all of the data that's coming at us, there are a tremendous number of questions that we can't really ask. And that's just because, frankly, our computing isn't up to the snuff. It's not there to the point where it can answer those questions. And so we are literally facing an inflection point. We are either going to have to suck it up and make a significant transition in the way our computers operate and the way we use our computers, and hopefully sort of get back into a situation where performance per buck is continually decreasing, or we wind up sort of trapped in a world where actually things are just going to get more and more expensive, and we are falling further and further behind the amount of data that's rushing in. So that's sort of externally what's helping to drive some of these issues. You heard some of these numbers earlier about the amount of data that's being generated and that people would like to collect. It turns out that today, the rate at which people are attempting to collect data anyway is roughly increasing 1,000 times faster than the increase in the manufacture of transistors. All right? So what happens is that people are collecting data like crazy, and for the most part, the vast majority of it is being thrown away because there's no place to put it. And even if there was a place to put it, there's no computer that can actually get its arms around all that data and do something with it. You know, one of my favorite examples is the City of London. They've got 600,000 closed-circuit TV cameras that are running 24/7, and how much of that data actually lives more than 1 week? Practically none. So all of this data, they're huge expense to collect it. They don't have any place to put it. They don't have any way to analyze it. And so this, you know, this situation is either going to change, or we're just going to be so inured by it that we're just going to let the data wash over us and say the hell with it. There's another issue that's going on simultaneously with this dramatic increase in the amount of data coming at us, and that is the fact that our computing architecture has not changed since 1948. And there's a reason why it hasn't changed. If you sort of look at all of the computers that have existed over time, I would characterize them, or I would call them, von Neumann architecture Turing machines. Von Neumann architecture is what Johnny von Neumann back in the late 1940s and 50s essentially codified, but he viewed this architecture as something that shouldn't last more than a year or two. It was just something that he did so he could get his first computer built and running. Right? And so what is the von Neumann architecture? It's having a central processing unit with some sort of small, fast amount of memory around that, and then a storage system further away, and everything essentially gets shuttled through the central processing unit. Well, think about it. I mean, that's the way our computers work today. If von Neumann came back to life and saw what our computers were, he'd be outraged. He'd be furious with us. He'd say, you mean you guys had all of this time and you couldn't do anything better than that? My kludge? Okay? And it's true. The other issue is that they are Turing machines, and Turing machines are wonderful. They can compute any number that can be computed, but it turns out that there are a lot of states, there are a lot of things that can't be computed. And so Alan Turing, whose name is associated with the beginning of software and the beginning of computing, all along wanted to get away out of that paradigm, and he wanted to build machines that could find answers to questions that couldn't be computed. We don't have anything like that today. So here we are, still with von Neumann architecture, Turing machines, after 60 years. And why is that? Why is that? Well, in large part, the reason is because we have been on a treadmill. And that treadmill is called Moore's Law. So much of the energy and resources and creativity of our entire industry has been so focused on making transistors smaller and packing them, more of them, onto a circuit that we have simply not had the energy, the ambition, or maybe in some cases the perceived need to actually fix a lot of the background problems that computing have had all of this time. We just got sort of fat, dumb, and stupid and thinking this is great, this is going to happen forever, and I don't have to actually think or I don't have to do much. My computers are just always going to be better. Well, guess what? That's not true. It turns out that, you've heard this before, I'm sure, but in fact, the end of Moore's Law is nigh, really, this time. It turns out that today, the top-ranked semiconductor manufacturers are making semiconductor chips with the smallest feature sizes at 14 nanometers. That is about 40 atoms wide. Now, everybody agrees, everyone who's in the field agrees that it should be possible to build chips with feature sizes down to 7 nanometers, or transistors, and they'll still work. The problem is that the cost is going to go up exponentially. And so there's a big discussion now about, okay, Moore's Law is essentially over now, deal with it. Or some people say, no, wait. There's 2 more generations left. Well, okay, big deal. I don't care whether it's now or 2 years from now or 4 years from now. Moore's Law is over with as far as we're concerned. And so we need to figure out how to adjust to what comes after that. Do we just sit on our butts and continue to do the same thing over and over again from after that? Well, of course, as a company, HP says no to that because, you know, we want to continue to be refreshing things every 3 years or so, right? So we want to stay on an exponentially increasing potential or computational capacity, but we're not going to get the free ride from Moore's Law to do it. And so many people are essentially happy. They're celebrating. They're saying, actually, the end of Moore's Law is probably one of the best things that's happened to the industry in a long time, because finally we can get out of this hole, out of this rut, and start really getting serious about understanding what computing really is, how to architect systems properly instead of in this really kludgy fashion that it's been for so long, and really start to understand how we can solve problems. How we can solve problems efficiently and fast without having to go through a lot of the unbelievable hoops that we have to go through right now. So, my approach to this, in fact, I have been anticipating this and working on this for almost 20 years. And trying to put into place for the industry and for Hewlett-Packard a set of solutions and options that would be usable after the end of Moore's Law. And I think that I and practically everybody else has been rather amazed at how long Moore's Law hung in there. It has been a remarkable engineering feat. But now that we are seeing the end of it, these other technologies are starting to become very viable and very important as we understand how to make truly better and very different machines. And so what we're looking at is optimizing the function of various components within a computer based upon the natural physical laws that we have available to us. And so we have a mantra within Hewlett-Packard, and that is electrons compute, ions store, and photons communicate. And what the heck does all that mean anyway? An electron, of course, is a very, very tiny, fuzzy piece of charged matter. It's extremely light, and it's like a Nerf ball in some sense. And it can move down a wire at almost 1/10 the speed of light. But the fact that it's charged is great because you can push it around with voltages. And that means that you can cause it to perform tricks for you. You can get it to do computation for you in a very, very small volume just by tickling it with voltages. And so that's fantastic. Ions, what are they? Well, ions are atoms that have had electrons removed from them. So now all of a sudden the ion becomes charged. And because it's charged, you can also apply electric fields to it and move the ions around. And it turns out, and I'm going to get into this later, that's an interesting way of storing data. And then finally, photons. Well, what are photons? They are particles of light. So when you look up here and you see a light bulb, actually what's happening is that there are a stream of particles, if you will, that are coming in and hitting the retina on your eye and causing little chemical reactions, and that's how you see. Well, it turns out that, of course, photons move at the speed of light. They are very fast, and you can put many, many different colors of light into a very small area, so you can carry huge amounts of information. And so what we are doing is we are looking to essentially put these technologies together to marry them into hybrid systems where each one is performing its function in an optimal way in order to build a new generation of computers and break away from effectively the tyranny, if you will, of Moore's Law. Now, electrons actually have been the main engine of computing for 60 years, and I don't actually see that changing. There's a lot of reasons for it, but really electrons are the ideal carrier of information when you're actually performing a computation. So we don't think that's going to change, but what is going to change is essentially the nature of the processors that are used for doing the computation. So we see a transition more and more to what are called systems on chip. That's a single chip with a large number of processors on it. And of course, you're aware that exists today. There are many examples of what are called multi-core chips. But the thing that's going to be changing is the fact because of the ability of, or the desire to adapt your hardware to your particular computational needs, we see that these cores are going to wind up becoming specialized. You will wind up having a chip with, it might have as many as 256 processors on it, and there may be 6 or 7 different types of processors, each one highly tuned to a specific task to allow you to take a particular workload and execute that workload most efficiently as you go through the system. Now, the issue is that in this highly parallel world, that can generate some significant programmer challenges. And so on the software side, one of the big things is trying to make sure that your operating system and all of the sort of layers built on top of that make all of this complexity in the computational world completely transparent to an end user. We want to be able to have somebody come in, and even though the machine itself, the computer, is undergoing revolutionary change, which is really dramatic, we actually have to make this look evolutionary to the end user so we don't scare them off and have them run away. So we're having to, on the one hand, it's like, it's schizophrenic. We're doing this really revolutionary stuff, but oh, don't worry about it. It's just going to be, for you, it's just going to be, faster, cheaper, all of this other good stuff. But really, there's going to be a tremendous amount of work that goes in to making this thing look at the end user and make it look like something that's familiar to them, and bring them along on the journey as we make these things ever more capable. Now, today in computers, I have a loud natural volume, so I think I'm going to lower this a little bit. Today in computers, most of the data is actually stored using electrons. Electrons are great for computing, but they're actually not very good for storing information because they are these tiny little particles, and what's happening is that the data, or the electrons, are essentially stored by putting them in boxes. These boxes are getting smaller and smaller all the time. In fact, they're getting down to the range of size where now, all of a sudden, quantum mechanical effects are starting to come into play. Effectively, the wavelength of the electron is starting to become the size of the box that you're trying to put it in. And when that happens, something called the Heisenberg uncertainty principle comes into play, and the electrons want to escape. They want to run away and hide. As we try to drive the size of the boxes smaller, the electrons are more and more anxious to get away, and so you wind up having to sort of hold them in some fashion. And the way you do that is by expending energy, by putting some electricity into the chip. So what that means is that now, in a lot of, especially high-performance computers, most of the power being expended by the computer is not actually being expended by the processing chips. It's being expended by the DRAM, just to hold the electrons in place. So that's actually not a good thing. Using electrons to store information reliably is getting very hard and expensive, and so we need something else. We need to do something different. So that's where ions come in. Ions are, as I said, they are atoms from which we have removed a couple of electrons to make them charged, but as far as quantum mechanics is concerned, an ion is just a great big fat lump of matter, and it's classical. It's a classical mechanical particle. And so if I take an ion and I park it someplace, I go away and I stay away for 1,000 years, and I come back, that ion is still where I parked it. All right? And it doesn't matter how small the box is. You can make very, very small boxes, and because ions are heavy, they just don't run away from you. So, what we're doing is we're building devices. And Meg mentioned a name earlier, and it was mentioned before, called memristors, that are based upon putting ions in a box and moving them around. And so it turns out that the electrical resistance of the box depends upon where the ion is inside the box. So if I put an ion in a box, and I'm sort of show 2 boxes down here, I guess this thing doesn't show up on the screen very well. Sorry about that. If I put the ion up close to the top of the box, it turns out that it then has one particular resistance. And if I move the ion and I put it down in the middle of the box, it has a different resistance. I can measure that resistance and tell between a 1 and a 0, or I can actually move that ion in smaller increments in different places in the box and measure the resistance, and I can store more than 1 bit of information in the box. So we've actually been working on this for quite some time. I started this research in 1998. Doing new technologies is hard. It takes a long time. We're now essentially with a partner fabbing chips that we're sampling and looking at, you know, in full 300 millimeter or 1 foot size wafers. You know, we still have a ways to go. There's still a lot of development to be done. But the issues are that this type of storage turns out to be almost as fast as DRAM. Not quite, but almost as fast. It is much cheaper than DRAM. It is much higher density, and it is much lower energy, much lower power consumption in the system. And so because of the density advantages and the cost advantages, we think that by essentially just using more of this, we can essentially hide the speed issues with respect to DRAM. And we are seriously looking into, I'll just say on the very short time frame, building computers in which we replace the DRAM with these Memristor chips. Shortly after that, we plan on essentially expanding out and going to higher and higher capacities and replacing the hard disks in computers as well with this same technology. So all of a sudden, you now have a system in which you have these chips with a lot of wiring. And this essentially is showing you a schematic and a electron microscope picture of a cross-section through one of these chips. And it turns out that we can take these boxes, these ion boxes, and we can stack them up on top of each other, and we can address them all on a single chip. So the total theoretical number of bits that we can store on a single chip actually gets up to be somewhere around a terabyte of information in a single DIMM size form factor. That's not going to be the first product that comes out. It'll take a while to get there. But that's where we're going to, and that is so much higher data density than anything else that we're aware of, that we feel confident that this is really going to be a displacing technology, that we really will be able to utilize this in replacing the standard hierarchy. And so you know, what does this do? Well, what it does is it destroys the von Neumann architecture. It takes a system where you've got this hierarchy where you've got, you know, cheap spinning disks down here, but which are horribly slow and very, very energy intensive because the cost to keep those disks spinning is huge, and turns everything into one big block of sort of uniform memory and storage, or call it non-volatile memory, memory that just remembers forever. And every bit in the system, or every byte in the system, I should say, is addressable by any processor in the system. All right? So what we're doing here is we are completely inverting the sense of the old architecture. Instead of the processor reigning as the king and all the data having to be transferred to the processor, we're essentially building large blocks of essentially fast storage. And the idea is to essentially disperse the computing out through this storage. And so when you have big data, the last thing that you want to be doing is shipping data around. I was actually on a project a while ago where the fastest way, or the highest bandwidth way of moving the data from where it was being collected to where the people wanted to analyze it, was to load it into large shipping containers full of hard disks and bring in a helicopter every day to fly it out and move it. All right? So instead of that type of issue, having to move the data to the processor, the idea here is we move the application to the data. If you've got a gigantic amount of data, and it happens to be in a different country, if it happens to be in a different location, or even in a particular place within your data center, you move the application to the data. There are processors there, multi-core processors, that perform the operation on the data locally, so you're not moving things around very much, and then what it does is it ships the answer back. And that turns out to be a far more economically viable way of performing a calculation. Now the next part of the puzzle is actually photonics, or photons. Photons destroy distance because it's light, it's moving at the speed of light. And you can essentially put a photon into a really nice piece of clear glass here in Napa, and you can ship that data halfway across the United States, the continental United States, before you would have to actually try to take that data and amplify it in any way. Now, people have known this for decades. I mean, our landline telephone systems have been operating with optical communications for decades. Why haven't we adopted this into the computer industry? And the answer is it has been far too expensive. In the telecoms industry, it's still the case that the value of the information that's being transmitted is so high that they can afford to do things in onesies and twosies and have an awful lot of handwork that goes into assembling the photonic systems for the telcos. In a computer, in one of today's computers, in a rack, there is more data flying around the backplane of a modern-day computer rack than there is on the telco lines in the entire North American continent. So it's clear that we can't use the telco types of solutions for the computing, and for decades we've been struggling to figure out how to get away from essentially the tyranny of the telcos. Of course, would love to sell their stuff to us, but who wants to spend 100 times more for the backplane than for the rest of the computer? So what we've done within my lab at HP is we have essentially learned and figured out how to do the same type of thing with photonics as we've been doing with electronics for decades. We're doing integrated photonics. We have learned how to take the same types of processes and systems, and we actually use silicon chips to create photonic circuits that are made by standard CMOS types of processes, thereby bringing the cost way down, decreasing effectively the cost of these systems by a factor of 1,000 or more, and at the same time dramatically improving bandwidth, latency, and cost per bit, energy cost. We actually had to go, because there's no industry around this, because the telcos don't want to do it, they want to sell us their existing solutions. So we've literally had to go in and invent every part of this chain within our labs, including the machines that do the packaging for the system. And this just sort of gives a little bit of a illustration here. On the bottom left there, you see one of the machines that we've built to actually take chips and package them into a system. A silicon processor chip, for instance, and what's called an optical engine, which is the system that generates the light that we use for all of the communication. And so we actually have an automatic system that does what's called flip chip and bonds these things into a package so that we have a complete system. And this is now starting to roll out. We're starting to bring this up in manufacturing partners so that we can have this ready in a fairly short amount of time. Now, what this does, by destroying distance, what the photonics do is it allows us to build, I'll say, very, very large data centers in which we have massive amounts of memory and a large number of processors, maybe even 1 million cores in the data center. And by having this photonic fabric, we're able to build systems where literally any processor in the entire data center, in this case there's over 1,600 racks that are shown here, any processor can access any byte of information anywhere in the data center. And it can do it in a couple of microseconds. Okay? That's how long it takes in order to get from one side of the data center to the other. So effectively, as far as the system is concerned, I mean, we're able to, by this combination of dispersing the processors within the data and then having the fast light wave communication system, we can take an app, we can send the app out to where it needs to be, perform locally on the data, and then at light speed send the answer back to where it needs to go. And if there's data that's in other places, it's accessible by random access, again, at light speed. So what do we call this thing? Well, we call it the machine. I put HP in there because I'm trying to distinguish between Turing machine and other machines. But this is the biggest project that we've had within HP Labs in 20 years or more. This is the biggest thing that we've done within the company and as essentially a dedicated research project since we introduced RISC over 20 years ago. Meg mentioned it's taking half the resources of HP Labs plus a lot more, and Meg has been piling on the resources to make sure that we do this. It's explicitly a non-von Neumann machine. We sort of display it here in a fashion to sort of highlight the different technologies that go into it, the electronics, the photonics, and the ionics. But really, you should think about this as being interspersed and interlinked dramatically as a single block. So the machine is for us a magnificent challenge. We are exercising every bit of our capabilities as an organization, all the way down from what my group is, which is the fundamental physics group, all the way up to the high-level software stack. And in fact, as much as I am a hardware guy and I love the machine itself, the thing that you can touch, 2/3 of the people working on the project are doing software because that turns out to be the bigger thing. It will have a Linux option at first so that the OS won't seem too strange to people. But we are looking at a new operating system because in order to take full advantage of the capabilities of this, we're just simply not going to be able to do it the old-fashioned way. So this is the project that we're working on. And what I always wind up getting asked about is, well, what comes next? What comes after the machine? Well, here is where I get to speculate a little bit and get a little bit wild and crazy because after all, I started thinking about the machine almost 20 years ago and started trying to put the pieces of the puzzle together then. And now people are asking me, well, what happens 10 years from now or 20 years from now? Well, what the machine is going to do, if you sort of take a look at the way we've architected it out, it actually kind of looks like the human brain. Because in the human brain, you don't have a central processing unit over here, and you don't have memory over here, and wires sending the data back and forth. What you've got is sort of a uniform system where, in many ways, the memory is the computation. So what we're starting to really seriously investigate now, and really going all the way back to Alan Turing's work in the 1940s, and we're asking, what's the next thing? And what Alan Turing actually wanted to build was something that he called an O machine, where O means oracle. Now, why? Well, because Turing and a guy named Kurt Gödel back in the 1930s completely destroyed mathematics in that era by demonstrating that there were problems that could not be solved within a set of instructions that define a particular computational system. What the heck does that mean? It means you can't get there from here, even though there's a there. And Kurt Gödel essentially had this wonderful statement that if you think about it, it's just absolutely crazy. So the way that Kurt Gödel demonstrated that this was possible is he came up with a statement that says, this statement is false. Now, if it's false, well, then it's true. But if it's true, it can't be false, right? And so this is what Captain Kirk always used to destroy the minds of these alien computers with all the time, right? The writers of Star Trek knew about Kurt Gödel, and so they're always putting Kirk in these situations where we could destroy a computer by positing sort of tricky questions like this. Now, I mean, this is an example, sort of an existence proof, but it turns out that there's a wide range of problems for which there are almost trivial answers, but it's either impossible or extremely difficult to compute what that answer is. And so an oracle machine would be a machine which has both the standard types of computational capabilities that normal machines do, that a Turing machine does, but then it also has some type of an oracle. In other words, the machine is smart enough to realize that it might be stuck, or maybe it's seen this problem before, or maybe it just has a flash of insight and says, hey, I can take this thing over here and I can take this thing over here, and if I put them together, I have an answer to the problem, but in fact there is absolutely no formal computational way that I could ever get from A to B. Okay? And so that's actually one of the things that we're seriously thinking about and proposing is building an oracle machine. Something that actually takes your problem in a problem statement instead of an algorithm, parses that statement and says, do I know how to solve this? Do I go do it in a brute force fashion by just setting up a computation and calculating it? There are certainly many, many problems that can only be done that way. But there are other ways in which it could cheat, like Captain Kirk, cheated on his final exam from Star Trek school or whatever it was. What do human beings do? If they don't know something, well, they'll go ask. They'll ask an expert. So if you have a problem, and one possibility is that your computer just goes out and asks its friends, have you ever seen this before? Do you have a solution to this that I can use, that I can borrow and build on? Or maybe that computer has actually solved that problem before, and the answer is already in its memory, in this great big vast memory, but it has to be able to find it. Or maybe it just guesses. Maybe it has the possibility or the potential to guess a solution, and then it will guess many different solutions and then sort of compute backwards and see which one is the correct one. All right? So when you think about that, when you think about the possibility of being able to literally cheat and guess or find a solution to a problem, and you ask what's the savings in energy and time of being able to do that, well, it can be astronomical. Yeah, I mean, you can destroy all of the types of thermodynamic arguments people have made about what's the limitation of computing if you can just say, oh, my computer actually knows the answer to this problem. It's got it there. It doesn't have to compute it. It just fetches it and brings it. Okay. So I hope you were at least mildly entertained. I don't know how much time I've got, but if there is some time for questions, I'd be delighted to take some. Yes?
Well, as somebody whose whole career was based on Moore's Law, I'm very sad to hear of its demise. So, but since I'm getting close to retirement, the fact that it's ending is probably not a bad thing. But, as a company that does test semiconductors, this machine would look like it's got tremendous testing challenges to it. Has your team been working on that aspect as well?
Yes. I mean, because so much of the machine is new and different, we have not only had to build the underlying technology, we've had to build all of the test capability as well. You cannot take a Memristor and put it on a semiconductor parameter analyzer. It blows up. It doesn't know what's going on. I mean, what's actually hilarious is you can put a Memristor on a semiconductor parameter analyzer and it will drive the parameter analyzer into oscillations. And that was actually something that we had to figure out. So we've had to build all of our own test and measurement equipment. We've had to make all of our own data analysis protocols. We've had to do all of the theory to make the models that we then give to our circuit designers so that they can design circuits around these things. And then we've had to come back and look at the reliability issues. So literally, I mean, one of the reasons doing something like this takes more than a decade is because of all of the infrastructure that goes around it. It's not just the device itself, it's everything. And then, of course, working through partners to get it manufactured. So it's been quite a journey. It's, if I had known back in 1998 how much effort this was going to be, I probably wouldn't have taken the first step. It was only that I was really stupid and naive back then that I even got started in this in the first place. And have managed, somehow to stagger forward and get to this point.
So this might be a little bit out there. Current incarnations of something like this, if you look at IBM's Watson, it has storage that it pulls from existing data. So
yes.
That's how it's able to pull up with answers. Are you thinking about possibly putting something in this to where it can ask itself questions? as opposed to like right now with a SQL Server data system, you ask the question, it caches the answer. So if you ask that question again, it can get the answer back.
Yeah.
But if you were to put something in like a Fermi equation, anything like this, and it can store it and give it itself the ability to just posit through all of these different things so that the answer could already be there.
So either you have read Turing's Cathedral, or you are very prescient, because there's an entire chapter in the book that talks about some of these types of issues. Let me say, first of all, that I am not a big fan of sentient machines. I don't want a sentient machine, and at least the present understanding in the field is that in order for sentience to exist, an entity has to have a model of itself in its environment. And my view is I want to deny any machine that access. I don't want machines to have models of themselves in the environment. And so at some level, I don't really want the machine asking originating questions. But what I do want it to be able to do is when it is asked a question, to then be able to follow a sequence of inferences and propagate out into a system and literally realize, again, have I seen this before? Essentially recognize. Is it something that I can I guess an answer, or do I have to go ask, do essentially a web search and see if there's something out there that's been doing it. And so that's sort of keeping things within a shell, shall we say, of denying the machine a model of itself in its environment. So once it starts asking questions on its own, then there are certain aspects of it that I'm not comfortable with following that train.
Quick follow-up.
Yes.
If it's supposed to follow a logical procession to understand and find this answer, couldn't the next logical question be, I wonder what his next question should be? So
well,
follow that?
Let's put it this way. You are asking some absolutely front range questions on the bleeding edge of information science and computing, and you're absolutely right. I mean that is a potential outcome, and I think that what we want to do is my own view is that I want to proceed cautiously. I mean, in George Dyson's book, he actually has a little chapter in it, and what he says is that if computers become sentient, we won't know it. The entire World Wide Web could become sentient in a microsecond. The transition from non-sentience to sentience could happen so rapidly, and the machine itself, the entire system, could figure out what the consequences of us learning that it has become sentient so fast that it would never let us know. Okay, so we're playing with fire here, right? I mean, you can get burned, but on the other hand, if we hadn't had fire, we wouldn't be where we are today. So this is an issue. Go in with your eyes open, understand what the consequences are, and deal with them up front. But those are great questions you're asking.
Great, thanks, Dan.
Thank you.
Great discussion. Okay.